The next few topics we cover are all going to involve light, and for quite a few years, scientists debated whether light was a particle or a wave because depending on the experiment you do, you seem to get different answers. Around the beginning of the 20th century, when quantum theory was finally put together, scientists realized that all matter really has both wave and particle characteristics. So the universe turns out to be more complicated than classical physics would have suggested. We first look at geometric optics, which is where light moves in straight lines until it encounters some kind of change in material, and that's pretty much what light from a laser pointer will do. Wave optics, and then finally light as a particle or a photon. So in geometric optics, the way we measure directions is from the normal, and remember that means perpendicular to the surface. The simplest rule in geometric optics is the law of reflection, which just says the angle of incidence equals the angle of reflection. So if you look below on the right, you can see here's our normal, the black line. The light comes in the bright purple, and then it goes out as this fainter purple. This angle here is theta I, the angle of incidence. It's the angle that the light makes with the normal. And this angle here, theta R, theta reflected, is the angle the light exiting makes with the normal. And these two are equal. So just theta I equals theta R is that law. The reason it works, it's the same thing a basketball would do if it doesn't have any spin to it and you bounce it off a wall like this. The x component of momentum doesn't get changed, but the y component gets reversed. And that makes it go in at this angle and come out at the same angle. So the same thing's happening here. The component of light parallel to the mirror doesn't get changed, but the perpendicular part gets reflected. So this is probably the simplest law in all of physics, theta I equals theta reflected. This also explains why a mirror and bright white copy paper look so different. In both cases, they're reflecting almost all the light that falls on them, but they don't look alike at all. And the reason is roughness of the surface. If you could see the surface of a mirror, if you could measure it, you'd see it smooth on the level of millionths of a meter. So any bumps would be very, very small. The paper feels smooth, but the highs and lows on its surface are much, much larger than micrometers. So on the left, we see a bunch of light rays coming in, hitting a mirror. They all come in and leave at the same angle, so they start parallel and they leave parallel. On the other hand, on the right, a piece of paper might look like this rough, uneven surface with these normals, these dotted green lines pointing in many different directions. And every time the light hits, we still have incoming angle and reflected angle being equal. But since the normals are all over the place, this means three incoming parallel lines go out at all sorts of different angles. So on the left, the mirror, this is called specular reflection. And on the right, we call that diffuse reflection because the light is diffused in a variety of directions. If you want to think about this in terms of people passing basketballs, imagine you got three pairs of people just bounce passing balls on a flat gym floor. You'd pretty much get this picture on the left. On the other hand, if you take them outside in a rocky field and have them do it, where the ground is all over the place, you're liable to see those balls go in a variety of different directions. So just like hitting a mirror is a change for our light beam, going from one material to another also causes a change. And to understand this, we need to introduce the idea of index of refraction. We've seen before that all kinds of electromagnetic radiation, that's light and IR and radio waves and X-rays and all that, travel at the same speed in the vacuum of space. That's not true if they're traveling through matter. Light gets absorbed and re-emitted by the atoms in whatever, glass, plastic, water, whatever, and that causes a delay and it slows it down. And the net effect is a change in the effective speed of light of that material. So we can write the new speed as v is c divided by n, where n is the index of refraction. Since it's the ratio of two velocities, it doesn't have units. A vacuum has n equals 1. Air, depending on temperature and pressure, has n very close to 1, maybe 1.0003. Water has an index of refraction of about 1.33, and there's all sorts of different kinds of glass that you can't really pin down one fixed value for it, but a lot of times in the book it'll say 1.52 for glass. Diamond has one of the highest indices with n equal 2.42. What this means is light goes much more slowly through diamond than it does through air or a vacuum. Now, even though it's very slow, it's slow by a factor of 2.4, which is about 40%. 40% the speed of light is still pretty darn fast, but the fact that it slows down has some significant effects. Because air and the vacuum are so close to the same value of n, we usually just use 1 for air just for simplicity because it's such a small difference. It's kind of like the way we ignore air resistance a lot in Physics 1. If we have an interface between two optical media, like let's say we're talking about the surface of a pool where air and water meet, we'll have the standard reflection here, the theta I and theta reflected are equal, but some light is going to go into that pool, and we know that because if you are swimming and you go down underwater, it's not like you're plunged into darkness. You can still see because there's still some sunlight coming through the water. You also know that there is some light leaving the water because if you're standing on the edge of the pool, you can see people who are in the pool. Now, the light that goes in the pool will be we call the refracted wave. This means it's slightly bent as it goes into the water. If you look here, you can see theta I and theta reflected are the same size, but this light going into the water is much closer to the normal than the light entering the water. So this theta refracted is a smaller angle than theta reflected. Now, if you were in the pool and you had a waterproof laser and you decided to shine it out at this angle, theta refracted, so very small angle, when it left, it would retrace this line. So these arrows, you could reverse them and you get the same thing. Light goes the same way. When it leaves the water, it moves away from the normal. When it enters the water, it moves towards the normal. And that's because of the general rule that if you go from low index of refraction to high index of refraction, you get closer to the normal. But if you go from high to low, you move away from the normal. The formula here is not a lot more complicated than the thing we had for reflection. This is called Snell's law, and it connects these angles and the indices of refraction like this. So index of refraction up here times sine of theta 1 equals index of refraction in the water times sine of this angle. Notice that we don't have incident or reflected, refracted, whatever on these. We just have 1 and 2. And the reason is we get the same path going in as out. As I said, we could have the laser down here and it would follow the same path. We can put in some numbers here and see what kind of results we get. Let's say we have a beam in air coming in at a 30-degree angle to the normal. What's the angle underwater? Well, we would say 1 for the air, index of refraction, sine of 30, equals 1.33 for water, sine of theta 2, and we'd solve it for sine of theta 2. When we do that, we get 22.1 degrees, which is, of course, smaller than 30. It does get bent towards the normal. This is the same way, by the way, if you want a mechanical analogy for this, if you imagine you're riding in a wheelchair on a cement driveway, that's low index of refraction, you can go fast. If you look at if this is the wheels and the axle, as they move towards grass, the first wheel that touches grass is going to slow down, and the other wheel that's still on concrete will swing around. So you get the wheelchair bending towards the normal here as it goes into the grass. If you were leaving the grass, the first wheel that gets on cement, this one, the right one, would be moving faster and you'd turn this way. So it's a pretty decent mental model. Now there is one twist here. If we're inside the material with a higher value of n and we try to shine the light out, We already saw that if we aim the beam at 22.1 degrees to the normal, the beam leaving the water is 30 degrees to the normal. What about if instead of shooting, almost up over our heads, we shoot the laser way out this way, a very large angle with respect to the normal? For example, 60 degrees to the normal. What do we get on the outside? Well, we do all the same math, only this time we solve for theta 1. 1.33 times the sine of 60 is about 1.15. This one for index of refraction of error doesn't matter. We have to do the arc sine of 1.15, but your calculator won't do that for you because sine is bounded by +1 and -1. Arc sine of 1.15 doesn't exist. What this is telling us is the light can't leave the water in this orientation. It's just going to bounce off the surface and go back down in the pool. And that's called total internal reflection. So this only happens when you're going from a high value of n to a low value of n. All of the beam bounces off the surface of the water and goes back down into the pool. There's a critical angle where this first happens. I mean, we can see 22.1 was fine, 60 was not fine. Where's the dividing line? Where does this first happen? The way we could figure this out is we could say, what's the first place? N sine theta equals 1. So we would write, what's the arc sine of N2 over N1? And for water, that gives us arc sine of 1 air over 1.33 water, and we get 48.8. Now, if you saw this formula on a test on the formula sheet and thought, oh, I can't remember which is N1, which is N2, the only way it will work is if the smaller value is on top and the larger value is on the bottom. Otherwise, your calculator won't do it. Now, you can try this yourself. If you've got an aquarium or something like an aquarium, you look through one side of it while it's full of water and you can see out the back just fine, but you should notice you can't see out the left or right sides. They look like they're mirrors. You can have your finger right outside the left or right side and you won't be able to see it. Now, if you lick your finger or get it wet and touch the side of the glass, all of a sudden you will be able to see it. You'll see a fingerprint made up of the color of your skin and what looks like a mirror. The reason for this is your fingerprint has ridges and valleys. The ridges touch the glass and they're the thing you can see, and they'll cause what's called frustrated total internal reflection. What that means is the light's able to cross this very skinny area, this thickness of water, between your finger and the edge of the tank, and it would not really be allowed to be there, but if the distance is really short, meaning not large on the scale of its wavelength, it can travel across. It gets absorbed into your finger, and some of it gets radiated back or reflected back, and you can see your fingerprint. On the other hand, the valleys in your fingerprint, they're too deep for the light to be able to cross and get to your skin and bounce off. So you just see the mirrored surface. So the valleys are regular total internal reflection, but the part pressing up against the tank, the fingerprints, that the ridges are actually frustrating that total internal reflection. You can see this a lot easier if you use microwave optics instead of visible optics. You can get a microwave optics kit, and what you see is that light going across this region where it's not allowed is quantum tunneling. So if you have a microwave optics kit, what you can set up is you've got the transmitter here in blue. If we got rid of this gray thing, we would have a big reading out of this microwave receiver on the right. It would be shooting straight across this gap into this receiver, and the little indicator needle would be maxed out. When we put this prism here, we get regular old reflection, just like we saw theta I equals theta R. It would come in there, it would bounce off there. All of the microwave energy would go into this lower detector, and none this way. Now, what about if we add another one of these prisms, this 45-45-90 prism? We put it here, and we notice if we get it close enough, what we start to see is we're not getting any more out the bottom. It's all going straight through. Even though there's this gap here, if there was no gap at all, we'd just have a straight cube, and we would expect the microwaves to go straight through just like light goes straight through a window. But when we have this gap here, because the microwaves have a wavelength in the centimeter region, this gap can be big enough to stick your fingers in, and you still get transmission here. So it's classically not allowed to be in this region, in this gap, but it tunnels across. It's basically quantum mechanical tunneling across from one prism to the next prism and then out the back. As you bring them closer together, this happens. You move them far apart. It gradually returns to everything bouncing off and going down here. What's going on is the index of refraction becomes a complex number. It has a real part and an imaginary part, and that means the intensity of the microwaves decays exponentially here. So it very quickly goes to zero. But if you get this wax prism close enough, it can go across that region where the intensity got very small and sort of rebound and make it through.